Okay, let's get started.
You ready? Or solo versus Manchester United?
Yeah.
We're gonna be rivals here. Oh no, I guarantee that Barcelona doesn't hold. It's obvious. 100%. United sucks.
Okay, so we're going to continue our discussion on the area problem. So, we're going to cover a few important examples today, but most of today is going to be, one of those days where I'm just going to be giving you a lot of theory that is going to help us set things up later. But we really want to attack the area problem. So remember that was figuring out how much space something takes up. And we decided that a long time ago we figured out, just dissect this thing with a bunch of shapes that you know how to find the area of, and add up all these shapes. Area of all these shapes. Now we want to move from that idea, something that of course a human being could do pretty easily, and a human being could add up all these areas, because that's very effortful and intensive, and we don't want to hire people to do this for a living, because that would not be, it's not very efficient, is one thing. But then when you try to take this idea and condense it into some sort of formal, concise, neat mathematical theory, it turns out that that's a little bit harder than you'd like. I mean, ultimately you are going to learn how to do something like this when you get to multivariable calculus, but for now that's it's too complicated. There are a lot of things that human beings could do relatively easy, but once you try to condense it into a list of instructions, it can be quite difficult. Some of you might know about this, but like Google's AI failed a math test the other day. Did you guys hear about it? Like all these engineers are like developing this AI that's going to crush this math test, and it failed the math test. Because it turns out that there are things that a bunch of 10 and 11-year-olds and 12-year-olds can do that if you try to tell a computer how to do it, it's very difficult. So yeah, for us, describing this is too complicated. We're going to actually want to simplify this a little bit. It turns out, what does it mean to draw a vertical or a horizontal line? Too many things to worry about. Let's just kind of make it a little bit simpler. Let's only worry about slicing it vertically. So we condense the problem to this, and we're really going to want to be measuring the area of these strips. Now ultimately I'm going to want to be able to use calculus on this and everything we know about functions, so you'll notice that if I threw this on an xy plane, we automatically have an issue. It's not a function, because it doesn't pass the vertical line test. So this is also too complicated for us. And so what we'll do is you will say, you know what? Let's look at a half of it at a time. Let's ignore the bottom for a while. And so now we have something that looks like a function, and we can have strips on that. And even that was too complicated, because now the tops have these very irregularly shapes. Each part has a different shape on top of it. Too complicated. So we decided to make it even simpler. So we've condensed the problem to the following issue. Sure, we're going to slice things vertically, but we're going to make sure that each slice is a very nice thing. We're going to slice off the tops horizontally to create rectangles. Right? And so this is where the solution to the area problem begins. We will solve ultimately the area problem, the guy we really want to get at, by first looking, how will we find the area under a curve with rectangles? So that's going to be where we start. Simple. Let's start here. Okay. So now, let's look at that. How do we actually do this? Now it turns out there are tons of ways to draw rectangles under curves for this purpose. So that's the first thing we're going to want to talk about. So we'd like to approximate the area under this curve using rectangles. This is where our journey is going to begin. It turns out there are several ways to do this. here are some popular ones. Right? These ones are all the rage in Calc 1. One way we can do this is called using right-hand endpoints. So pretty much we want clear instructions on how to construct these rectangles, and here's one way that we can construct rectangles. Okay, so I'm going to draw a random function here. Here's my function f of x. Suppose I want to find the area under this curve on this interval. One way I can do that is to, like we're saying, dissect this interval, like chop it up into little itty-bitty pieces, and on each one of these pieces I'm going to create a rectangle. Now one way to create a rectangle is for you to say, for each of these mini intervals that we have, let the right side determine the height of the rectangle by just going up and coming across when the right side hits it. So with this, I hit it with the right side, and that's the height. Hit it with the right side, that's the height. Hit it with the right side, that's the height. Hit it with the right side, that's the height. So this is called constructing the rectangles using right-hand endpoints. So basically we have an interval that we care about, and we cut it up into smaller intervals. So this is the interval that we care about. We cut it up into smaller intervals. Each of these guys are called a subinterval. And on these subintervals, we erect rectangles with the rule that the right side plugged into the function determines the height. And this is called using right-hand endpoints. Notice here, we get an overestimate of the area, because the area under the curve would be this. Notice that if I were to measure all the areas of the rectangles, I'll be getting extra areas here. So here, in this particular case, right? Because our functions are increasing, the right side is always going to be higher than the left side, so this would cause an overestimate. But it's one way we can estimate the area. We'll get a slightly larger answer than the actual answer though. So maybe you don't want to err on the side of getting a larger answer, you want to err on the side of getting a smaller answer, and so you can set up rectangles using left-hand endpoints. So basically, you can have the same kind of function, you care about it on this interval, and again, you cut up that interval into subintervals, and now you take the rule that the left side plugged into the function creates the height, left side plugged into the function creates the height, left side plugged into the function creates the height, left side plugged into the function creates the height, left side plugged into the function creates the height. Well, now notice that if I measure the area of these rectangles, I will actually get smaller than the actual area in this case. But the left side creates the height here. In this case, we get an underestimate. So that was one way to create rectangles. We can use the right sides or the left sides. Now, maybe you kind of, for this particular function, wanted to have less error in some way, so you might consider another way of creating rectangles. One that would kind of be self-correcting in some sense. And another common way is to use midpoints. So we can look at the same kind of function. Here it is. It's your function. You can dice this up into several sections. You can create all these sections. But now you decide, you know what, we're going to use the middle of the rectangle to create the height, the middle of the subinterval. So you pick a middle point here, and that creates the height. Pick a middle point here, and that creates the height. Pick a middle point here, that creates the height. Pick a middle point here, that creates the height. Pick a middle point here, that creates the height. Now you'll notice that when you do the midpoint on this particular example, of course you're not getting a perfect approximation, but you kind of have this situation where one half of the rectangle will make an underestimate, but it's compensated for because the other side is going to make a slight overestimate. So this is just one of the ways that we can come up with to kind of minimize the errors that we have. This is called the midpoint rule. So we're going to be able to approximate errors using a finite number of rectangles like this. You will be required to do this on exams, and I can ask you about any one of these three paradigms for creating a rectangle. And they will each have their benefits or drawbacks for a particular kind of function. And but these are three common ways that we can create rectangles. And they will have varying degrees of success with various errors. Right? Now, of course, none of them are perfect, but we'll get to that in a second. But these are three ways to actually create rectangles. Bless you. Now, what we're going to do is, it's nice to have an idea and draw these pictures, but what does it all mean? How do we put this all together? Well, let's focus on something else here, the how-to. Okay, so let's look at this kind of function. I'm going to make some things more precise. Let's start giving things names. Suppose we call our function f of x. Right? Let's say the interval we care about is the interval ab. Right? Now, this is running along the x-axis. So a and b will be certain x coordinates. We will call these guys. We'll define them, and we'll number them. And you'll see why this is going to be nice in a second. It's called a. The first guy, x0, and then you would number them x1, x2, so on, until you get to b, which is going to be xn, right? N is going to be the number of dissections you're making, the number of rectangles you're erecting, or the number of subintervals, okay? So here, n equals number of subintervals equals number of rectangles. So we've come up with that notation. Now, what we will want to do is we want to make things, again, as simple as possible. So let's make sure all these subintervals have the same width. I'm going to cut up this interval into subintervals, n of them, of the same width. I will call this delta x. So that's going to be what we want. So here we're going to define delta x to be the common width of the subintervals. This would mean that delta x would be equal to, so you want to take the length of the interval AB, and you want to cut it up into n equal pieces. So how would you actually do that? Well, you'll take the length of the interval divided by n, and that will be the length of each piece. Now the length of any interval, any horizontal distance, is going to be right minus left. Right? Sounds like a very simple concept in Calc 2, that's going to be super important. Every time you're measuring something horizontal, right minus left. Measuring something vertical, top minus bottom. We'll get back to that. So the length of this interval will be b minus a. And I want to take whatever that number is, and I want to divide it into n equals pieces. I therefore obtain the formula that my delta x, the length of each subinterval, will be b minus a divided by n, where n is going to be the number of subintervals, which is equivalent to the number of rectangles that I want to use. So that's the first nice piece of thing we can talk about. Now, the next thing we are going to want to talk about is the x values. How do we find the xi? So I'm using I to represent the subscripts of these x values. So we can start by looking at how they're constructed. Well, of course, a x0 is just equal to the a value. Now to get to the next one, what am I going to do? Well, start at the a, add delta x, and that gets you to the next one. So I'm going to take a, I'm going to add delta x to it. How would I get the next one? Well, to the previous one, I added delta x to get to the next one. So if I want x2, that's going to be x1 plus delta x. But I can place this here for x1, and so I get this is just a plus 2 delta x. Similarly, x3 will be a plus 3 delta x, and x4 will be a plus 4 delta x's, and so on. So that in general, I'm able to say the xi's will be a plus I times delta x. That is going to be the formula that will give me my x coordinates. Now, when it comes to who we want to use to figure out the height, it will depend on the paradigm you want to use. So for example, if I wanted to use right-hand endpoints, that means on each subinterval I'm looking for the right number to plug into the function. So on the first subinterval, I would choose x1, and I would leave out x0. Second one, I would choose x2. Then I would choose x3, then I would choose x4, all the way to the end, I would choose xn. So for the right-hand endpoints, we can talk about the right-hand approximation for the area. This is called Rn. This is the right-hand approximation. For the area A. Okay. Now, what that means is the heights of all my rectangles will be given by the function evaluated at the right-hand endpoints, which means it's going to be the function evaluated at the first x1, then evaluated at x2, all the way up to being evaluated at xn. Those are all the heights, and I want to multiply height by width. So this is the height of the first rectangle times the width, height of the second rectangle times the width, height of the third rectangle times the width, etc. And so this gives me the right-hand rule as a nice concrete formula. In fact, I can even have a shortcut, a shorthand for this. I can use our summation, which we talked about in the last couple of lectures. And I can measure I to talk about the current subinterval. So I can go, I goes from 1 up to n, where I'm measuring these subscripts. It will be f of xi times delta x. And this is the formula that will condense the right-hand rule. Now in the finite case, you won't have to worry about being so sophisticated. You can definitely think about it that way. And we'll do some examples of that. But to actually write this down in a nice, condensed mathematical way, that's how you actually do it. So when someone says, what does it mean to do the right-hand rule? It means to compute this summation. That's what it means. We can do this for the other two. Actually, I left this up here, but let's just do, so here's A, which I'm calling x0. Here's the B, which I'm calling xn, and I'm cutting this up into x1, x2, etc. Okay. Now I can talk about the left-hand way of doing this. It's going to be very similar to the right-hand way of doing it. All you're going to do is you're going to figure out something that we call ln, the left-hand rule approximation using n rectangles. So in this case, each subinterval you're going to pick the guy on the left. So in the first one you're going to pick x0, second one you're going to pick x1, third one you're going to pick x2, etc. All the way down to the last subinterval, you're going to pick xn minus 1, the guy just before xn. This guy will get left out. And so we'll have f of x0 plus f of x1 plus dot dot f of xn minus 1. You stop 1 before the last guy. You're multiplying all of these by delta x, which is going to be the width of your rectangles. And that's you summing up the areas of all the rectangles. Or in other words, you can condense this by saying sum I goes from 0 to n minus 1 of f of xi times delta x. And that is the left-hand rule. Where the xi's are given by the formulas that I just derived. When it comes to the midpoint rule, there's a little bit more calculation that we need because we have to figure out what's the middle. So call this m sub n, it's midpoint approximation to the area, and we are going to call this f of x1 star. It's usually how they do it. Some people do it f of x1 with a bar over it, but I believe your textbook uses star. So plus f of x2 star plus all the way down to f of xn star times delta x, where xi star, we want this to be the middle, the midpoint. Okay? So which means for the midpoint rule, these are the guys we're looking for, the guys in the middle. Right? So this is your x1 star, and that will be your x2 star, etc. But how do you actually compute these guys? Well, the point that's exactly in the middle of two numbers is given by the average of the two numbers. So the mean average, so that's all we're going to do. So to find x1 star, what I'm going to do is I'm going to take x0 plus x1 divided by 2. That's going to give me that number. And then once I find that one, I just keep adding delta x. It'll still be a delta x distance between these guys. So starting with this number, add delta x to get all the other numbers. And so in general, I can say xi star is given by xi minus 1 plus xi all over 2. Where the xi's were found using the previous formula. And ultimately that condenses into this, which I can write in a summation by the same I goes from 1 up to n of f of xi star times delta x. So those are the rules in very concise mathematical language. So we did it pictorially, what it would mean to actually set it out as a human being. If you wanted to actually state this as some abstract mathematical fact, this will be the way you would state that fact. So let's actually do this. Let's actually do an example here. So, like, what would I actually ask you to do on a test, and how would you actually write it out? Let's jump into that. So, here's an example. We'll go something like this. It'll ask you to approximate the area under some curve. Approximate the area under the curve. Let's say I told you it was 6x minus x squared. For x equals 0 to x equals 6. So I'm on the interval 0, 6. Using n equals 3 subintervals. Or I can just say 3 subintervals. Equivalently, I could say using 3 rectangles. Equivalently, I could say using n equals 3, right? I could say this phrase in several ways. 3 subintervals is equivalent to me asking you to use 3 rectangles. That's equivalent to me saying n equals 3. N represents the number of subintervals that we want. Yeah.
What is that a subscript or a comma after x equals 6?
Comma. Yeah, sorry. It's a comma. So find the error under this function on this interval using 3 subintervals, and now usually I ask you about only one of these, but we're going to do all 3 just so you can see the differences. Right-hand endpoints. Right, so that could be a question. Find the error under this on this interval using 3 subintervals and right-hand endpoints. Or I could ask you, find the error under this using left-hand endpoints. Or I could say using midpoints. So let's actually see how we would actually, let's see how we'd actually do this. Now it's going to be easier than what I wrote down before. You don't have to be that theoretical with it, but the theory is needed to develop things that we want to develop later. So let's say for A. So a nice way I like to set it out is to actually draw the interval and like identify who I really care about on this interval. So I'll just draw a picture. Label it 0 to 6. They told me I want to split this into 3 equal parts. So now it might be obvious to you what those parts are. If it's not obvious, and you kind of want to know this anyway, you find your delta x. Your delta x is going to be b minus a over n. Your a is always the leftmost interval number. Your b is always the right. So this is going to be 6 minus 0 over 3, because I'm told to use 3 subintervals. So this means the length of each should be 2. So 0 plus 2 will give me 2, 2 plus 2 will give me 4, and those are the x coordinates that will give me equal length subintervals on 0, 6. Now, because I'm using right-hand endpoints in version A, I want to pick all the right numbers, as in the ones that are on the right. Those will be those 3 numbers, right? So I look on the first interval, 0, 2, 2 is on the right. Second interval, 2, 4, 4 is on the right. Third interval, 4, 6, 6 is on the right. So these 3 numbers will get selected, the 0 will be left out. And now, all I want to do is basically say what the approximation is. R3, my area is going to be approximately R3, which is, well, it's going to be f of 2 plus f of 4 plus f of 6. All of that times delta x. And at this point now, I just plug in what all of those are. So my f of x is this. So f of 2 is going to be 6 times 2 minus 2 squared plus 6 times 4 minus 4 squared plus 6 times 6 minus 6 squared. All of that multiplied by 2. And then you would compute that, and whatever, the answer goes here. And here you'd actually get a whole number, but if applicable, the fraction form is preferred. That's how you actually do it. I mean, we haven't allowed calculators for a while, but I'd allow you a calculator on this one to actually compute that number, in case it might be slightly annoying. But that'll be it. That's the right-hand rule. All the theory built up led to this. That's basically it. The others are very similar. So I could look at the left-hand way of doing things. Again, I draw that interval. 0, 6. I know I want to cut it into 3 equal pieces. What is the length of those pieces? Well, it's b minus a over n, which is 2. So I know I start here, keep adding 2. Then I'm going to choose the numbers that the appropriate numbers. On the first interval, 0 is on the left. On the second interval, 2 is on the left. On the third interval, 4 is on the left. Those are the three numbers that I would pick. So the area would be approximately equal to the left with 3 points. It's going to be f of 0 plus f of 2 plus f of 4 times my delta x. That would mean I would take 6 times 0 minus 0 squared plus 6 times 2 minus 2 squared plus 6 times 4 minus 4 squared, all of that times 2, and I would get the answer. That will be the approximate answer. And clearly that will give you a different number from this one because you're evaluating different points. Here you're evaluating f equals 6 instead of f equals 0. They'll give you different approximations. But they're both targeting the same thing. We might also talk about the midpoints. It'll start out innocently like the others, 0 to 6. Have all of these. You'd have your delta x equals b minus a over n, which is 2, so that's 2 and that's 4. But you'll remember that I actually don't want those ones, I want these ones. I want the numbers smack dab in the middle here. So for the x1 star, I'll simply average these two numbers, 0 plus 2 all over 2. That'll be 1. So 1 will be my first starting number. And then I would keep adding to delta x. So 1 plus 2 is 3. 3 plus 2 is 5. And those would be the right numbers. And so I can also approximate the area using the midpoint with 3 rectangles. And that will give us, well, f of 1 plus f of 3 plus f of 5 times our delta x. 6 times 1 minus 1 squared plus 6 times 3 minus 3 squared plus 6 times 5 minus 5 squared times 2. I'll give you whatever. So that's how you solve one of those problems. Now you won't be asked to do all 3, but I'll pick one at random. Say, hey, do the left hand, or do the right hand, or do the midpoint. You should know how to set up all 3. The midpoint just requires a little bit of extra setup in the beginning, but it's pretty much the same kind of treatment afterwards. Pretty much split up your interval, pick the appropriate numbers, plug into your function to get the heights, multiply by the delta x to get the width. Questions? Now, these are just approximations, and of course, you're not going to get a good approximation of some curved thing using 3 rectangles. So, this is nice, it's something we can do, but ultimately it's not satisfactory. You'd want way more than 3 rectangles, and who's going to sit down and do this for more than 3 things? So, we want an approximation anyway. How about we can find the exact area? So again, this is the gold standard. It's a pretty weird to describe in general, but we can describe it based on taking the simple situation and then really enhancing the simple situation. So here's the idea behind finding the exact answer. One thing you will notice is look at some thing that you want to find the area, and say you cut it into 3 sections. Take the left, left, left. Okay, so you're missing like huge pieces of the area here. Okay, so you might say, let's do more. So you go over here into that main. So now you can do that, and that, and that, 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 and that. You'll notice that you're missing actually a lot less. Right? You only miss this chunk on the last one and a huge chunk. And so the idea is the more rectangles, the better. Now clearly, even in this situation, you could enhance this by doing even more rectangles. Right? Instead of little gaps, but you'll have less. You can do more rectangles. But every time you throw in a set of rectangles, there's some guy down there in the accounting department who has to be adding up a whole other line of numbers now. Right? So that's not going to be very nice to him. So we want to come up with a nice way. And of course, because we're mathematicians and we don't really care about practical stuff really, we're like, let's just use an infinite amount, man. So the best. Let's just throw an infinity. Let that accountant earn his pay, right? Best is use an infinite amount of rectangles. Infinite number. If you have spaces, fill it in. You will have an infinite amount of rectangles to do. Eventually, you'll have this situation where you just keep throwing in rectangles. Missing space, don't worry, throw in more rectangles. Oh, still missing some space? Throw in more rectangles. We have a lot left over. And you just keep throwing them in. Eventually, you're not really going to miss anything, because every time you miss a space, you can throw in a smaller rectangle and make up that space. You'll ultimately get, in theory, and this is something that we have had to check in hindsight that this would work theoretically. In theory, you would get the exact area. You wouldn't have any spaces that you couldn't fill in if you can throw in an infinite number of rectangles. So basically what you do is you let n approach infinity, right? Because infinity isn't actually a number that we can like plug in and calculate. So what you do is use a limit. Let n approach infinity. Equivalently, and some formulations of the integral will take this approach. You could let the delta x approach 0, right? Let the width of each rectangle get smaller and smaller and smaller, and then you can do that. But we're going to do this formulation. So basically, the idea is, so here's the main idea. This is going to help us solve this version of the area problem, finding the area under a random curve. Well, you start with a Riemann sum. We mentioned that last time with the Riemann sum. That means you're approximating the area with the sum of the areas of rectangles. That means you're approximating area with a sum of things that look like this. Right? Where I is going from 1 up to n, for example. So that's you're using a Riemann sum with n rectangles. But you know what? Let's make that even better. Let the number of rectangles we're using go off to infinity of this summation. And that's going to give you the exact area. Of course, you have to prove that that gives you the exact area, but in top 1 we don't prove that, right? This is just the idea that we're using. Fill in all the gaps with more rectangles, right? So ultimately, if you want to use the first principles of Riemann sums to find the area under a curve, this will be the kind of thing you'd have to compute. Now, you won't be given this or that, so let's make it a little bit more precise. using the formulas I derived earlier, basically what I'm saying is this will be I goes from 1 up to n of f of xi. Well, what's the xi? Well, you're going to take the left endpoint plus I times delta x. You say, what is delta x? Well, delta x is going to be b minus a over n. And that's how we will find the area using this expression. Now that's a mouthful to actually write down, and even though we have our sigma notation to make it really concise, that's a little bit too wordy. You know, it's kind of like the math equivalent of a run-on sentence. You kind of want to shorten things up, make it a little bit neater. And so we have an actual short notation for this. This notation is due to Leibniz. So in his version of calculus, this is how he called it, and traditionally, that's how we call it now. We don't really use Newton's notation here, but he defined this notation, so the limit as n approaches infinity of the sum I goes from 1 up to n of f of xi times delta x. Well, he's a mathematician after all, so he's not going to name it something really fancy. He's like, what am I doing? I'm summing up a bunch of stuff. I'm finding a sum. And, oh, S is for sum, so let's use an S. So he used a very elongated, elaborate S. Because it wasn't just a normal sum after all. He's summing up an infinite amount of things. He has to make it look, snazzy. He wrote a snazzy S. And on this S, he decides that he's going to identify the interval. So he says, okay, the left endpoint I'll put at the bottom, we'll call this A. The right endpoint I'll put at the top. The function under which I'm finding the area, that's f of x. And I'm going to be finding it using an approximation of the change in x. And so we end up with this notation. So this guy means this sum. It's kind of like how we use f prime to represent this weird limit that we did, the limit of the difference quotient. In the same way, we use this notation as a shorthand for an infinite sum. And so here's how a lot of people were computing integrals before we had some nice ways, before they knew about the fundamental theorem of calculus, but they could write it down as a shorthand this way. And of course, you'll notice I use the same kind of notation as we did for antiderivatives. And that's because we have the benefit of hindsight. We didn't know this was connected to antiderivatives in the beginning. We'll eventually learn that. But this is where it all started. We use this symbol, and this is called the definite integral. On the interval AB. This is the guy that allows us to find the area under the function f. Computing this summation, and we call that its notation. This notation due to Leibniz. And we'll stop there. So the important thing we did here was you need to know how to use the right hand, left hand, and midpoint rule. As far as this thing, we'll actually compute some antiderivatives using this next time, and hopefully we can ultimately derive the fact that this is somehow connected to antiderivatives. This is a new. See you guys on Friday.